Well, it's a great pleasure to be here, and I hope over this week we're going to have a lot of fun. And I've had a tremendous amount of fun with SPH. When we started, of course, I didn't know much about anything really, because I'd never taken a course in fluid dynamics. I'd never computed any fluid flow. I knew a bit about computing, but mainly for integrations actually. And then we discovered everything for ourselves. And sometimes you can start off knowing very little and just work it out for yourself. As somebody once said, when you're doing research work, you can first of all read all the papers, which I never did because I thought it might affect the way I thought about things. Or you can read nothing and just work it out for yourself as well as you can, or read a very little. Now today I'm going to talk about smooth particle hydrodynamics, and because it's been around for a very long time, 4 decades, there are a tremendous number of things that have happened in that time. And there is no way I'm going to be able to tell you in 2 lectures about all those things. You'd be bored actually, just wouldn't be able to keep up with what I was saying. So instead, what I decided to do was to tell you a few things, and I'd start with things that you know very well, but tell you some of the stratagems, some tips for how you can improve equations and get greater accuracy, and also the thinking that went into it. Because you start with something and you can think of other ways of improving it. And that's my aim. So first of all, I'm writing today because Daniel said it'd be a good idea to write. So first of all, I want to make sure. Can you read that at the back? Okay. Do we have any special lights that go onto the board? No. Okay. I mean, the light is pretty good, but it would be better if there was some more light here, but maybe you can't do that. Okay. These lectures are all concerned with solving equations like the acceleration equation, derivative following the motion, gradient of the pressure on density, plus viscosity, plus, and so on, other terms. Now, these are the equations we want to solve. They're partial differential equations. They involve time and space, and they are continuum equations. In principle, to put down all the information that's contained in those equations, you would need an infinite amount of data, because it's a continuum, and to specify the continuum correctly, you need information at every point, and every point there are infinitely many. So we can't do this, so what we do is discretize, but in addition to this, also heat equations, and so on. So we've got all these equations, but sometimes you can get away with something that's cheaper. For example, you can get away with, in most of the fluid dynamics that occurs in engineering, it's an incompressible fluid. They worry about thermal conditions, but others they don't worry about. Incidentally, for this, in engineering, they'd have mu on rho del squared V. That's the viscous term, which is the second derivative. All the others are first derivative terms. And the thermal heat equations also involve second derivatives. Now, we can't deal with an infinite amount of information, so our plan is to discretize. So let's just talk about. There are many ways of discretizing a system. One, with a grid and information at vertices of the grid. Great thing about lecturing is that you don't have to write everything down. You can use words also. Now, grid, the information at the vertices, when we started with SPH, everybody, not entirely everybody, but almost everybody used finite differences. And in astrophysics, they used spherical coordinate systems because stars are spherical. And all they wanted to do was to look at them collapse. But Bob Gingold and I wanted to deal with binary stars and stars colliding where the stuff goes everywhere. And we could see that it was a waste of time using spherical coordinates, because how do you know you're going to get a collapse to the center of your spherical coordinate system? So I would say to these people, what happens if you have a star collapsing out in the edge of your beautiful spherical grid? And they don't do that, of course, because they feel that that's too difficult. So anyhow, they use grids. Of course, these days there are ways of handling grids which can do many things, but you mainly use Cartesian coordinates. So there are grids. Now, apart from grids, there is, let's see, Fourier series, which are spectral methods. And in addition to Fourier series, the ones that we were concerned with were how to use particles to discretize. And at the time, in the big defense laboratories like Los Alamos, there was a method called particle and cell, which had grids. For example, here's a grid. Particles inside, particles moved and carried information. It was then mapped back to the vertices of the grid. Finite differences were carried out on the grid to calculate things like grad P and del squared V. This was mapped back to the particles, and then the particles would move with the new velocities. So these are the principal ways of discretizing. Now this is the one which we're thinking about, and it has particles have many computational, gosh, I'll write out the whole word, computational advantages. Steve, do you think this shows up in Facebook? Maybe. Okay, particles have many computational advantages. Let me just mention some of these. I've got a little, well, obviously very complicated flows. Complicated flows. Can you people at the back still read this? As I get moving, I'll just keep probably getting smaller and smaller. So, complicated flows. For example, wave breaking. But wave breaking is actually more complicated than you think, because when you go down the beach, you notice that when waves break, they create bubbles. They don't create bubbles of the same size. The bubbles don't stay where they're produced. Bubbles change the properties of the fluid. How? Well, if the bubbles are a few millimeters in size, it turns out that the second viscosity, the bulk viscosity, can increase by a factor of about 1,000 if they're just a couple of millimeters. So it can be quite important, and nobody knows how to deal with that. Of course, we have two.
Does the fluid become more or less viscous with bubbles?
More viscous, more viscous, more dissipative. What happens is pressure changes pump the bubbles, and they're doing work while that's going on. Very large changes in density, and you know all about that because that's the star formation one. Three, what have I got down for three? There are a lot of these. multi-phase, and the fourth one I put in is fragmentation. Now, getting back to multi-phase, there could be many of these things, solid, liquid and gas, but a good example of one would be, you just think about all the things you know, volcanic eruption. And fragmentation, say the collision between planetesimals in the newly forming solar system, when you've got solid bodies hitting, so collisions of, I'll just say collisions of rocks, but I was really thinking planetesimals, but also fragmentation occurs if you've got a job in a mining company and they want to know something about if they set off an explosion here or there, what size the fragments will be. And they want a computation of this. They'd like to know if they're this big or they're this big, and of course there's a distribution of sizes. You can calculate that, but you have to have a slightly more complicated equation than this, because you have to put in the equivalent of, it's not just grad P, it's a stress term, and you have to put in some information about fracture. I can remember when I started thinking about fracture, it was, how did I get involved with it? I can't remember now. But we were working on fracture, and I thought, well, I don't know anything about fracture. So I went to the library, and there were just shelf after shelf of books on fracture. I knew enough about fracture to know that almost all these books are wrong because they didn't know how to calculate it. And it was much better to calculate things and have relatively simple models. You've got to have courage not to believe everybody. Now, having said all this and said that we're going to look at these particles and knowing that we can solve many problems, you can really solve many problems. We need a procedure and the procedure basically is quite simple. We forget the continuum, we replace the continuous fluid by particles. We have a prescription for getting the forces for the particles. I mean, there are forces here. We need to calculate the forces, so we need some procedure for doing this. The simplest procedure would be to say, well, we want to find grad P, and we want to specify initial density, and then we'll work out the density. I said also heat equations, but also we have a continuity equation. Also heat equations. See, go back to your notes now and add in something. I sometimes call the continuity equation the convergence equation. You see, this I call the acceleration, not the momentum equation. Just keep that in mind. The continuity equation involves the rate of change of density is minus rho div v. Now you know div v is divergence. So obviously minus div v is convergence. It tells you just how material is converging. So we need to calculate the forces. And I think I had a third one here. Follow the motion of the particles. particles, PTCS. Now, of course, all of you know this, but the trick with SPH is to figure out some way of calculating the forces efficiently. And when we first did this, it wasn't very efficient, and it really was an excessively long time before we figured out how to write down the equations so that they conserve momentum, linear and angular momentum, and other particular properties of this. So now we want to start with, and I'll just go over what I call the basic, I can't really get in there, so I'll put it on here, basic interpolant. Now the basic interpolant starts with something which is exact but useless. It's like many things in pure maths actually. Here's something which is exact but useless. This integral is over the space that you're interested in, and this is a delta function. Now, this is supposed to be the properties of the material. What you'd like it is the point R. But the delta function, you can't work out that integral because delta functions have the property that they're zero everywhere except they're infinite in a certain way, where R is equal to, where their argument is zero. And just to remind you, the integral of delta R minus R dash, this is a volume element, by the way, is equal to 1. Now, because we can't integrate this, what we do is replace it. By what we now call the kernel, which has some length scale, and typically we'd have a kernel which, this is in one dimension. So it's a one-dimensional kernel, and I think I had red here. Here's red. This is something which I've drawn in a rough way. It's a delta function. It's supposed to be infinitely high and zero width, in the sense that it actually has a width, but the higher this gets, the smaller that gets. And it's such that because it only has a value when R is equal to R dash, you replace R dash in here by R, take it outside, then the integral is 1. So that's all there is to it. Now I learnt about estimating various quantities in this way from somebody who was in Cambridge at the time, professor of statistics, and the statisticians wanted to be able to calculate probability distributions from samples. Think of samples as points in the space, but anyhow, from samples. And they made use of effectively this kind of interpolation. So now we use an approximation. We replace that and we have A R is equal to the integral of AR dash W R minus R dash H. Now there's a lot of things in here I need to mention, but I'm not going to discuss in any detail whatsoever. Like, is that really an equal sign? No, it isn't. That's an approximation to this function. What about H? How big is it? Is it constant? I'm not even going to talk about that at the moment, although it is always an issue. Now, we want to calculate this. So this, still everything, I'm not changing anything. W, now I'm going to divide it by rho, R dash, the volume element is here. This is the volume, this is the density, so that's kind of a mass. And Now I'm going to replace the thing by particles. I don't know that I wrote it down here. I want to say something about the kernels. I'll go further with that in a minute. So here we could have, and we do have, splines. They're the usual ones. Two Venlin functions, or three, you can construct others out of orthogonal functions, but I haven't found any use for those. So these are based on orthogonal functions. Thog. So what we want to do is evaluate that for a fluid, and we're going to take the fluid, here it is, and replace it by the continuum by a set of particles. Here are a few of them, 6 actually. So the whole fluid is replaced by these particles, and each of them has a mass. So this is particle A and has mass ma. When we started doing this, I didn't want to use I and J as labels and tags for the particles, because I have I as the square root of -1 and J, I don't know, I decided not to have that. And so I used other letters like A. And one of my friends said to me, you can't use A, or as it will turn out, B, because they aren't integers. And, but anyhow, they're labels. So these are going to label particles. And then I'm going to approximate this because I know that this is a mass. So this is approximately the sum over all the particles. I assume that they're in. And this will be A, B, W, R minus RB. This is very... When you use chalk, it doesn't slip. When you use these pens, they kind of slip. That turns an R into a gamma, but it's actually an R. And this is a mass. And down here is rho B. And that tells me, gives me an estimate of A at any point R. So that's the basic interpolation. Strictly speaking, if that's, I could walk out of here now and you could, using that, you could reconstruct the whole of SPH. But you'd need to think a bit. But that's the basic idea. Now, for any particle, therefore, if I'm at a particle, I can get particle at RA, the particle at A has the property A determined from a summation. There is one particular case of this which is pretty obvious when you write it down, and I'm just going back to this one here, and I'm going to replace rho by A. Let me use my red one now. So I want rho at R. I go across to this. A is now rho. Rho cancels rho. Then I've got these W's. MB, sum over all the particles, W R minus RB. Ooh. Now the thing about this is, it's approximate, but you can find its gradient exactly, because if you want to differentiate this with respect to any one of the coordinates, on the right-hand side, the only place it appears is in here. So you can just carry out exact differentiation. And that means that if you have a whole set of particles, and you want, here they are, here are some, oh, well, they're over here. Now, if you want to find the density here, you sum over the masses and the kernel for all these points. So if that's an R, these have got coordinates, and you can find the separation between those. So that's quite simple, and that actually is also used by the statisticians to calculate a probability density from a sample, except they don't have mass. If they've got n samples, they just have 1 on n. And they use various kernels. So I had a chat to David Kendall in Cambridge at the time, and he led me to the literature, and he's a nice guy actually, David Kendall. He's a famous statistician, but actually he started off working in astrophysics. He's really interested in astrophysics. And he went down to the Greenwich Observatory, and I think he spent a year there working on these problems. And then some aspect of it got him involved with statistics. The other nice thing about him was that he also liked books written for teenagers. I mean, sort of about 16 or 17 or 18. So he suggested that I read one of these books. And he said, see if you can work out the code. And in it, this young guy sends his girlfriend a final message, and it's in code. And it's actually quite a tricky code. And I remember David Kendall because of these kernels, and also because of the time I spent trying to work out this code. I don't know how the guy's girlfriend worked it out, but she might have known the key number. All right. Now, so now we want to apply this to something. And what we need to do is apply it to an equation like this. We now could calculate the density anywhere. So we could particularly calculate it at one of these particles, say particle A. We just put Ra in there and do a summation over all the other particles. Where they're closer together, more or less, the density is higher. Where they're far apart, the density is lower. And what we'd like to do is calculate this. I think this might rub things off. So let's try. Yep. In so doing, it makes the board changes colour to grey. This is going to be the rate of change, that's the acceleration of particle A, and these are going to be some forces. So I want to talk about this one. We won't talk about the forces that occur in fracture, and we're not going to talk about the forces that come from magnetic fields. We haven't time to do all this, but actually for clever people, and I assume you all come into that category, for clever people you can figure that out. So I'm going to consider calculating forces. I don't want to use this. And I gave this a heading, so I should actually have a look. Application to the Euler equations. So the Euler equations are just this and this, plus a continuity equation and maybe some heat equations. So we need grad P on rho. It's not very good. Let me try another one of these. Now for grad P, the most obvious thing to do is to write P in this sort of interpolation form and then take its gradient. What could be simpler? So, at particle A. Well, first of all, P at some point A, R is equal to, we just put P in here. So it'd have P on rho and grad W and M. So this, the equal sign, I'll just say it once more, is really an approximate sign. So that's the sum over the particles, MB, P at B, so I assume that we know the pressures at the particles, the density B, and then there's the W of R minus RB, and H. I'll occasionally remember to put in H. And then you can find its gradient. I'm allowed to play with these colours. Grad P on R, which is a vector, is the sum of all these guys MB, PB, rho B. When I take a gradient, the coordinates are only in here, so it becomes the gradient of W. And for particle A, grad P for particle A is equal to the sum over MB, PB over rho B, grad A. Now this W has an R minus RB, but I'm going to make that RA. So it's going to have an RA minus RB, and to save writing a lot of stuff, I write that as grad A of WAB. So a gradient with respect to the coordinates of particle A of a kernel which has coordinates RA minus RB. So that seems in a way all right. That means dVA dt is equal to dVA dt minus grad P on rho. Well, it's minus 1 on rho A. That's this one. And then this stuff that we've got here. And I'm going to write it all down. MB, PB, rho B, and grad A, WAB. So that's the simplest thing to use. But when you reflect on it, you will see that it doesn't conserve momentum, linear or angular momentum. And the reason is it doesn't have the right symmetry. And the force that particle A feels from particle B is different from the force that particle B feels from particle A. So there are two of us with, well, when we think about people, we'll think about particles. This does not, I'll just write this down. Momentum, linear momentum or angular. So what we need to do is find a form of this which will conserve these quantities. There I was in Cambridge thinking about this, and I knew that if you had a Lagrangian and it had certain properties, it would conserve linear and angular momentum, conserve other things as well. So what I did was write down a Lagrangian for this. I won't go into it at the moment. And then I got an expression for the forces, and then you can decode this and see what it is that it is in the continuum. No reason why I can't use this bit of board. So to conserve, what we do is we write 1 on rho grad P, 1 on rho grad P is equal to grad P on rho. This is one form of this, plus P on rho squared grad rho. Now you wouldn't think of that first of all. So 1 on rho grad P is grad P on rho. Think of differentiating this. This guy here gives you grad P on rho plus P grad 1 on rho. And this is equal to minus P on rho squared grad rho. And that cancels that one. So this has these two terms, one of which cancels this one, so it leaves grad P on rho. Well, I wouldn't have thought of that just sort of staring at this. So using a Lagrangian turns out to be quite good. Now, so instead of this guy here, which was our first approximation to minus grad P on rho, which came from this, we get minus the sum. Now I'm going to write all of these as if I had an SPH sum. So I'll take grad P, which I've got here. I'll divide it by, no, I won't do that. I'll take P on rho. So instead of P here, I have P on rho. And I'll put it in there and I'll have a P on rho squared. And then a gradient of that. And if you put it all together, this is an exercise for those students who haven't done it. You get this rather unusual thing. Now this guy is a Gaussian. Then its gradient gives you a vector in the RAB when you take its gradient. The gradient of this, say take d dx, you'll get an x term, d dy, get a y term. And that means that if you have A here and B here, you'll have a vector RB minus RA. And that's what you'll get from this. These are symmetric, except for the MB. But if you multiply this by MA to get a momentum, you will find that the total momentum vanishes. I mean, it's constant. So the sum there's a big sum here, sum of B, sum of A, MB, I've multiplied it by MA. I've got this thing here, which I won't put down again, but it's symmetric. That is, if you interchange A and B, it is the same. But this has this RA minus RB. I'll just put here. So that means when you do the double sum, this is invariant to interchange of A and B, but this guy changes sign. And it's the changing of the sign means that this thing, the total is 0. So this is if A and B interchanged, is equal to naught. So A and B are just tags, so you can interchange A and B and get the expression again, and it will be minus the first one. And it has to be equal to it. And if H is equal to minus H, then H has to be 0. All right. You've got this. And that means that you can actually calculate the dynamics, conserving linear and angular momentum. And all that you have to do is to be able to sum over the particles. Now when you do this, I'm now going to reduce the amount I write down. I'm not going to talk about accessing particles, except to say that for most of the engineering problems I've been involved with, you can do this by using linked lists in the three-dimensional space or any space. And that's the way, well actually the way we first did it was really to sum over all the particles. I think the first paper we wrote only had about 40 or 100 particles, and we thought it was very good when we had a few thousand. Why do we do this? Well, you have to remember that the computers that we had there would occupy half the space of this room, and they stored 1,000 words, typical millisecond cycle time, and so therefore you couldn't really deal with big problems. And we thought that if only we could handle a few thousand particles, we would be able to do some interesting problems. And of course, for every generation, you have your own ambition about what problems you would like to solve and what problems you can solve. And things just get better and better. When we have petaflop computers, we'll be able to solve another class of problems, but people will also think about new problems which are much harder to deal with. Anyhow, we only used a small number of particles, so we could just sum. Sum over A is equal to 1 to n, sum over B is equal to 1 to n for all of them. And then we started using linked lists for these, but of course in astrophysics you've got gravity to calculate, then tree codes came along, and then the tree itself can be used to access the particles. And there are other ways of accessing the particles, many ways of constructing trees, but accessing particles is quite important. If you can do that efficiently, that's good. The other thing is, this becomes a set of ordinary differential equations, one for each particle. Well, actually, if there are 3 dimensions, there are 3 for each particle. And you have to have some methods for time stepping so that you can evolve the system. That's another thing. What's the best way of doing the time stepping? Personally, I use methods which are based on a kind of leapfrog, symplectic. But in those days, we used a variety of methods for dealing with these. Now, there are various tricks that you can use to simplify everything. There are summations everywhere. All these summations and representations of functions. So what we'd like to have is some neat way of improving it, and I'll just mention one of these. But before I do, in case I miss out on this, when you construct the equations, this is the kind of advice old professors give to young students, try and construct them so that they contain important features of the actual fluid. Thus, if the fluid conserves momentum, make sure your equations conserve momentum, if linear and angular, if possible. If it conserves, say, you've got thermal energy equations, thermal energy, you want to get that right. But if you're looking at entropy, you want to make sure your equations guarantee that the entropy increases, as it should do. The rate of change of entropy, if you've got thermal effects, should be positive. Secondly, there are methods which are, well, other properties which you probably never think about. Vorticity. If you've got Euler equations, there's a quantity called the vorticity, which is conserved. It has infinitely many conservation terms because it depends upon integrating around any loop. So you want to incorporate those too. So that's the golden rule. Try and incorporate as many properties of the original continuum equation as you can in your discrete equations. Look at them and study them and try and think what you can do. Now, let me just take one of these. Maybe I'll use this one. For a start, it's white rather than a kind of grey. Let's suppose we want to construct div V at some particle A and use that interpolation. Well, we can sum over particles. We have a mass. We have a density. We have V of that particle, and then W, the kernel. Now, if you have a fluid, which even if it has constant velocity, you can't guarantee that div V is 0. It should be 0 for a constant velocity everywhere, but you can't guarantee that. But what you can do is, well, this is if V is constant, this should be 0. But it isn't in general. So what you do is, what I'm going to tell you now is a trick to make it better. This is the number 1. And I write an SPH form for this. MB over rho B 1, I'm not going to put it in, WAB. That's an SPH approximation to 1. Now I'm going to take VA times 1, which is VA just times that summation. I'm not going to do that. Hang on. I don't want to do that yet. I need grad 1. The gradient of 1 is the gradient of a constant, so it actually is 0. And that equals is actually an approximation. And I guess I should say that's 1 at the point A. That's what 1 should be at the point A. And I take a gradient with respect to the coordinate A. So this is not quite right. This is not quite right. This is not quite right, but I'm going to combine them so they're better. This is a case of 2 wrongs make a right. Somebody, an American, said to me, you can have 2 rights make a wrong, like somebody does something and they say this is the way it works, and then you say yeah, yeah, meaning no, no. All right, we take this and we subtract it from that. No, now I took a VA dot that, get this right in a minute, is VA dot grad 1 is equal to VA dot sum over B M on rho B, and it's going to be VA dot, and the vector inside here is grad A WAB. So it's actually VA dot that. I'm going to take this thing, which should be 0. And the reason it should be 0 is the gradient should be 0. But it isn't quite 0. But I'm going to subtract this from here. So I'm going to minus this VA. I'm going to dot it inside here. It's got not a summation tag. It's not a B. And all these W, M, rho, W things are all the same. So this is the sum over B, MB, rho B, VB minus VA, dot grad A, WAB. And that actually vanishes when V is constant, because it's got these 2 terms in it. So this is good. As I said, you've got 2 wrong things and you make a right. Well, you can put lots of things in your equations which are like that. I won't go into them, but I think it's a good idea to think about these things and ask yourself, is there some way I can make this better? Here's an exercise. Continuity equation. Show there are two forms of writing this. The rate of change of the density of particle A, notice this div V is equal in here, is either, just using what we've got there, that's this thing here, V is not constant, so that's just substituting, or the rho A dt, have I rubbed that out? Yeah, this one comes from having an expression for rho A, which I had down originally, and now it's unhappily disappeared, but it's rho A is just a sum, and you can get now in astrophysics usually you get the density just by summing over the particles, which is one of the things I wrote down first of all. If you're dealing with, say, a fluid in a tank or in a bottle, you see, this is better. Can I borrow this?
Yeah.
You see this surface. Incidentally, if you shake this, you get a flat surface all the time. You can show that, but that's neither here nor there. Now, the point is, if you're dealing with the fluid, it has a density of 1,000 kilograms per meter cubed, and there's just air up here. If you use the summation, then you get big errors near the boundary. So you have to have something that's a bit better than that. If you have d rho A dt, like one of these expressions down here, you can get much greater accuracy near a free surface. And if you're solving engineering problems, it's better to use one of these. And this one here, I prefer for this reason, that if you're going to take this form, which we've got from this, this is really approximating div V. Now, if you change all the particles and replace them by more massive particles in the same position, then their density will go up by the same factor. Let's suppose I make these masses larger by 1,000. Then the density, which we calculated for it because it's just a sum, will also go up by 1,000. So that won't affect this expression. Div V will still be the same. So if they've got the same velocity, but all you've done is scale up the masses, or scale them down, you should still get the div V, same div V, and that actually will give you the same div V regardless of this ratio. But this one won't. So if, for example, you were using those equations and you had two fluids, it could be you're modeling waves breaking on a beach and there's air and there's water, it's actually better to use one of these. It's just a question of thinking all the time, what is there in my equation? Will it still work if I change the masses? Will I still get this right? I'm looking for invariance in these equations.